Okay, so we're continuing here. This is the last slide we had in part one, and we found out that if you want to write down a law in this form where you integrate b.ds around a closed contour, and you want the right-hand side to be an integration over any surface that's bounded by the closed contour, this right-hand side had better be the same for every surface, or else you get a problem. You can't calculate this for different surfaces that are bounded by the same contour and get different values. That will be a problem. So let's try and see in general, is this expression the same for any surface that's bounded by the contour? Is it the same for all the surfaces? For instance, let's take the contour, this one, it's the same as this one. Let's take surface number one to be the surface that we see here. It's a nice flat surface. And surface number two to be the curved surface that's shown here. It's just important to imagine what surface two is. It's bounded by the closed contour. So it starts where the closed contour is, and then it goes out in space to form this open surface. Okay? So the question is integration of j.dA through surface number two the same as integration of j.dA through surface number one? Are these things the same in general or not? Let's look and see if we can find an answer to this question by looking at the two surfaces in the same picture. The two surfaces, what they do is they create some kind of volume between them. You can see here the volume that's above surface number one and below surface number two. This is a volume, it's a closed volume. Can you think, before you go on to the next slide, can you think what you can say about this closed volume in general? Take a few minutes to think about it to see if you can think of a way to address this issue. It has to do with the statement of local charge conservation, and you've taken this in detail before. If you haven't taken this in detail before, you should go back and study and read this, look at the videos on this part in detail, because you won't be able to understand what's going on here unless this is completely understood. So this is something we've taken before. We said that if you take any closed surface, this is a closed surface, the area vectors here are going from inside to outside. Okay, if you integrate j.dA through any closed surface, and the circle here means that it's a closed surface, it should equal to minus dq by dt. And this q is the charge inside the surface. And basically, just intuitively, just to remind you what's going on, but you should go back and review it, it's saying that if there's any current going through this surface, then the charge inside the surface must be changing. And there must be some relationship between these two things, because the only way for charge to change inside this volume is that the charge must be going through the surface. Okay, so go back and look at the slides on this part, and also look at the slides about charge conservation, local charge conservation, and global charge conservation, and what's the difference between them. So let's proceed, assuming that you understand this completely. So if you take this closed surface that's between surface number one and surface number two, whatever shapes they are, surface number one and surface number two, as long as they're bounded by the same closed contour, you can apply the statement of local charge conservation. You can say that integration of j.dA is minus dqn by dt. But the dA vectors, because it's a closed surface, they have to point from inside to outside. So that's why the area vector here has to point this way, and the area vector here has to point downwards, because it has to go from inside to outside. Now, if you cut up this integration over the closed surface into two parts, integration over surface number one .dA and integration of j.dA through surface number two, the dA vectors have to be pointing from inside to outside for this to be correct. Now let's see a trick we can do here. The surface number one, remember, we want the relationship between the ds vectors and the dA vectors to be very particular, obtained by the right-hand rule. And so the dA vector that we want to talk about when we compare the two integrals is this one, not this one. So it's very simple to get the relationship between these two area vectors. dA out points down and dA points up. They're just equal and opposite. So dA out for surface number one is minus dA, where dA is this vector here. That's the area vector that's useful for us when we're talking about the contour, the closed contour. For surface number 2, it's already in the right direction because it's already obtained in the correct way using the right-hand rule. So we don't have to change dA out. It's just the same as dA. So let's put these two things in the equation. So you get minus integration of j dot dA plus integration of j dot dA equals to minus dqn by dt. And now these dA vectors are the ones obtained using the right-hand rule and not the ones obtained thinking about the surface as a closed surface. This is a tricky issue, so if you have any questions about it, send me comments. So if you just rearrange the terms a little bit, you see that the surface integral through surface number 1 and the integral through surface number 2, they're not in general the same because of this term. This term makes them not the same. So what is the condition that these two surface integrals will be the same? Obviously, if this term is 0. We've seen before, what does it mean that dqn by dt is 0? It means that you have a situation of steady state. I've talked in detail about steady state before, so if you can't remember, you should go back and review it. But at this point, if I tell you that dqn by dt is 0, then you should immediately be able to understand that this is a situation of steady state. So it turns out that the surface integral for surface number 1 and surface number 2, they are exactly the same, only in the situation where we are in a situation of steady state, if dqn by dt is 0. An example of this is this example. So you have here a wire, it has a current in it, and the current is going to the right. And I'm going to make surface number 1 to be this circle, it's a circle. And then surface number 2 is some kind of open surface, that's a curved surface, that's bounded by the same perimeter of the circle. Okay, so I want to see, for this situation, we know that integration of j dot dA through this closed surface, the closed surface is formed by this circle plus the other surface. It forms a closed surface inside it. And integration of j dot dA is minus dqn by dt. Now, for a wire like this, there's no change in the amount of charge inside. So dqn by dt is 0. So that means that if you calculate integration of b dot ds around this contour, the perimeter of the circle, and you say that it's equal to mu naught times integration of j dot dA for any surface bounded by the contour, you can say this. There's no problem with this because this surface integral gives you the same value no matter if you take the surface to be this one, the flat one, or the curved one, or any other one. As long as the surfaces are bounded by the same contour, the integration of j dot dA will be the same for all of them. And this is why we were able to use Ampere's law in this form in the previous chapter for the whole chapter without any problems, because we were dealing in situations where we had steady state. So if you get the current going through this flat surface, it's exactly the same as the current going through this surface. There's no difference between them. So that's why you can state Ampere's law this way without any problem. But if you have a situation of where you don't have steady state, like this one, where you have a capacitor, and the capacitor is charging, for instance, this is the plus plate, this is the minus plate. I take my contour to be this perimeter of the circle. I take surface number 1 to be the flat surface of the circle, and then I take the curved surface to be the second surface. Now, if you look at surface number 1, and you look at what the current is through surface number 1, it's current I. There's a current going through, it's right here, the current's going right here. But if you take surface number 2, there's no current going through that surface. There's no conduction current. Conduction current means flow of charges. In the empty space between the plates of the capacitor plates, there are no charges passing from this side to this side at all. This is empty space, this region. So if you calculate the conduction current through the curved surface, you get 0. So that means that integration of b dot ds cannot be written as an expression, integration of j dot dA for any surface bounded by the contour, because if you take this surface, you get a value. If you take this surface, you get a different value. So you can't, this in general then is not true in general. It's only true in certain circumstances. It's only true in circumstances where this derivative is 0. And you can see why this derivative is not zero in this case, because when the capacitor is charging, obviously the amount of charge on this plate is changing with time. So this right-hand side is not zero. So in situations of when you don't have steady state, you cannot write Ampere's law in this form. We get to the conclusion that this relation is not true in general. If you want to write integration of B dot ds to be mu node integration of J dot dA through any surface bounded by the closed contour, this equation is not true in general. We already know that now, we proved it. So the question is, can we fix this expression or find an expression, maybe related to this, maybe by adding something, maybe by changing it in some way, and if we find this new expression, not this one, a new expression, that the integral over any surface will be the same, then that would be very useful, because if we now were able to find a surface integral that's the same for any surface that you take bounded by the same contour, then it's plausible that you could have a correct expression for Ampere's law that will be valid for any situation. So that's what we're going to look at in the next part.